Hello everyone. In this video we're going to discuss a bit more about planes, talking about the different types of equations for a plane in three-dimensional space, and then we'll do a little bit in Maple and in one example finding the equation of a plane. So as seen in our previous discussions and in the textbook, the general equation of a plane I like to phrase in this format here: ax plus by plus cz equals some other number d, where in this case n is a vector which is normal to the plane, has coordinates a, b, and c, so those are the coefficients of x, y, and z in the equation, and it also, we're assuming, contains the point x sub 0, y sub 0, z sub 0. So you got normal vector and you've got a point. With that information you can determine the equation in terms of x, y, and z for your plane. Alright, and you do that by just substituting in the coefficients for x, y, and z as the x, y, and z component of the normal vector, which we're denoting by a, b, and c, and then plugging the point you're given in for x, y, and z to determine the number d on the right side of the equation. Alright, and again, I wrote out what it is here. Don't need to memorize that at all. You do need to know the general equation of the plane, which we'll be using most often. You will see also in some textbooks what's called the point normal form of a plane. It's just a rewrite of the description up above there a little bit. All right, so it turns out the plane containing the normal vector n and the point p, which we're saying is x sub 0, y sub 0, and z sub 0, can be described by this equation, that the normal vector dotted with x minus p. So if you take a point, general point x, and you look at the difference between that point and that lies in the plane and the vector p, that will be a vector that lies in the plane. Well, if the vector x minus p lies in the plane, its dot product with the normal vector must be perpendicular, or must be 0, because those vectors are perpendicular. So you get 0 there, and if you just do this dot product, multiplying the first components, second components, third components, etc., all right, then you will end up getting the following equation. All right, that's just the dot product expanded out. So these two are one and the same essentially. We're mainly going to be, for our purposes, focusing on this version, or this equation right here. That's going to be the main one I'll be using. I do want to talk about the parametric description a little bit, and then I'm going to do some things in Maple before we get to an example. That description is perfectly legitimate. All right, but we saw a vector form of a line, and a plane is kind of the next simplest graph in 3 dimensions. So can we have a vector form of a plane? And it turns out we can. All right, there's a parametric description, right, which is in terms of vectors. Let's read through that, and then we'll do a little bit in Maple before getting to the example. So it's saying if you've got two vectors that are non-zero and non-parallel, I'm calling them u and v, all right, in 3-dimensional space, and then if we want to think about the plane that contains those two vectors, u and v, and some given point, which I'm calling p here, that can be determined by this set of points here, where you're taking the point p viewed as a vector plus linear combinations of u and v, meaning sums of scalar multiples of u and v. All right, so that's similar looking to the equation of the vector form of a line, but it has another parameter in it and another vector in it. All right, so the vector form of a line, remember, was, I'll just write it down, I'll jot it down real quick and then erase it. The vector form of a line was a fixed point or a fixed vector plus t times your direction vector, which we denoted by v a lot. So notice this is a real similar looking formula, except we have two parameters, which makes decent sense because a plane is something that's two-dimensional. All right, in that sense, this is a little bit more dynamic of a description of a plane versus the static one up above, where it's given just in terms of an equation. All right, so what's the differences between these? The first one, circled above, you need to know a vector which is perpendicular, or we also refer to as normal to the plane, to determine the equation. For this one, for this parametric description or vector description, you need to know a point in the plane still, and then you need to know two vectors that are non-zero, right, non-parallel to each other in 3 space, that lie in the plane, or that the plane contains. All right, so what we're going to do in this example, and we'll get to that in a little bit, is to find an equation of the plane that contains a given point and some given vectors. All right, before we do it, let's take a look at this in Maple a little bit. I'm going to graph a plane, and then we're going to come back and solve this example here. All right, so I've got Maple open here. I collapsed over here on the left side the palettes. You can open those back up, but I'm going to just collapse them for the video. So I've got most of this typed in. When we start any file, we're always going to load the plots package. So with parentheses plots, no spaces. If you load that, it loads. You have access to all these different commands. If you put the colon at the end, and then press enter in math mode, then that suppresses the output. So it still loads the package, but you don't see all of the commands that are there. All right, so I've defined a vector u and v here, and notice again we do u colon equals. I'm just going to redo this. Colon equals is defining things or giving things names in Maple. So we're going to do a less than sign and then 1 comma 1 comma negative 1, then a greater than sign, and Maple automatically turns that into vector notation. And then when we press enter on that, it defines u. I just multiplied it by t to make sure that it would multiply. Maple is putting this as what we refer to as a column vector. All right, that's just the way it's written, but we're going to think about this as a vector in 3 space. I've also defined the vector v here, and then what I did was I defined a function of 2 variables, which I'm calling capital P for the plane. Right, and then I'm going to end up graphing that. So this is essentially the formula that I had in the OneNote file there. So I'm t times the vector u plus s times the vector v plus, I just made up 1, 0, 0, negative 2. That's the point I'm using. All right, now I just checked that it worked by plugging in some numbers, and then what I did was I plotted it using the plot 3D command. So you can plot parametric surfaces, and we're going to be doing more with this throughout the course in Maple by using this type of syntax. You're going to put plot 3D in, and then you have to type in, I'm going to go back and do that again. You have to type in here an ordered triple involving the variables t and s, or whatever the parameters are that you're using. So if I went and did t s 2, then that would give me a different looking plane. So I'll just do that. But you have to type in an ordered triple, and then outside of that, your parameter ranges, whatever you call them. I call them t and s. So if I press enter on this now, it gives me this plane. All right, which is different than the one I actually want to plot. So I'm going to go back and change it again. If I put capital P of t comma s, then what that's going to do is it's going to plot this parametric surface, which is going to be the plane where I want to look at here. All right, now the reason it gave me that error is because I opened this file and I didn't reload everything. All right, meaning I didn't actually define this by clicking enter, by pressing enter on it. So you can, if I do that now, same thing for V, I gotta do it for V as well. Then if I go back and press enter on this line, it will graph it. A quicker way to do this is to hit the triple exclamation point at the top of the screen, and what that will do is it will reload every command in your file. All right, so there's the graph. All right, so I've got the graph of that. Now I've got it in the default view, which is the box view. We can change that as we've seen before. All right, so there's the plane. Now I've got a few other things plotted here I want to show you, and then we'll see if we have time to do that example in this video, or we'll leave it for the next video. So I also plotted, using the arrow command, the 2 vectors. I'm just going to show you that now. I've given this graph up above here a name so I can display it together with the next plot in a moment. I've called it P1, so I did P1 colon equals. Now that output has a name to it. All right, now when I press enter here, all right, I'm just going to take the colon off. So it's giving me 2 vectors. All right, now what did I do here? I'm basing these vectors at the point that we get by plugging t equals 1 and s equals negative 1 into that parameterization. What point is that? It's the point 2, 0, negative 5. All right, and it's basing the vectors there. Then I put a set of 2 vectors. I did 2 times u and 2 times v just to make them come out a little bit bigger. And now what I'm going to do is display that together on the same axes. All right, so now what we can see is we've got the plane, and we've got two vectors that are non-zero and not parallel to each other that lie in that plane. All right, so those are the vectors u and v. It's actually double the length of u and v, but again, they're in the plane. I've also plotted the normal line, and I'm going to show how to find that normal vector, probably in the next video. But the a vector, which is, I shouldn't say the normal vector, there's a whole line of normal vectors, but one such is given by this vector n, 3, negative 1, 2. So I plotted that line. All right, and that looks like this. All right, so I defined a new function, which I called capital N, and you do that function by, I'm saying t is being sent over, and keep in mind, remember how to do this arrow. You're going to do a single dash and then a greater than sign, and Maple converts it to the arrow, and it's t times the vector n, which is the normal vector, plus some point that I want to plot. I chose that one there. So it's going to have this, so it's going to be crossing through this base point for the vectors u and v. All right, now we plot that. All right, you got to do space curve, and then inside the space curve command, you got to put an ordered triple. The way I've defined this function n, it is an ordered triple, so I just put n of t. All right, and then we put in the parameter range, put the color. All right, now what I want to do is display all of those together. So the plane, the vectors u and v, and then the normal line. And there's the graph right there. Okay. All right. Now, one thing I want to point out is if you rotate this around, so if you did the same things, it doesn't really look like it's meeting at a 90-degree angle. And, all right, we can see that, yeah, it crosses through. Can we convince ourselves that that's really meeting at a 90-degree angle? Sometimes Maple, just for ease, will scale the axes, the x-axis, y-axis, and z-axis, in the most convenient way it sees fit for plotting purposes. If you want to make sure that you're getting the true view, you can use the option in the display command, which is scaling equals constrained. So type that word in, no spaces. Now when I do that, it changes the view a little bit of this. Still same graph, but now if I kind of rotate this, we can really see that it's meeting that plane at a 90-degree angle. So it'll show those angles more true. All right, so the vector I put down there was a correct normal vector for it. I'm just going to take that off now and press enter to execute that line. So again, once again, we see the plane containing the vectors u and v. We see the normal line in there as well. All right, and we're going to work out the example to find the equation of this plane in the next video.